So welcome to my series of videos on statistics. And in this particular video, I'm going to teach on hypothesis testing and estimation for population variances. So up until now, all the hypothesis testing we have done hypothesis testing for mean. And then we did it for one population, and we did it for two populations where we can have an independent sample or a paired sample. Then we have also done hypothesis testing for proportions. And for that one too, we were introduced to hypothesis testing for two population proportions. Now, in this particular video, the emphasis is hypothesis testing for population variance. All right, hypothesis testing for population variance. Now, remember, earlier in this series of videos, I taught on variation. And I said that every measure of central tendency must be accompanied by a measure of variation, okay? So if you remember, I taught on the measures of variation, and I said that when you do the mean deviation, you always get 0. So sometimes we square the mean deviation and to lead us to what we call the mean squared deviation or the variance. And because we squared it, we have to find the square root and bring it to the standard form, all right? And that is called the standard deviation. So the standard deviation is a measure of variation around the mean, all right? The standard deviation is a measure of variation around the mean. Now, there is no statistical test that tests the hypothesis testing for standard deviation directly, but we can approximate it using what we call the chi-square test. So in this video, I'm going to teach you how to read from the chi-square table. Now, what you must know is that standard deviation is the square root of variance. Okay, if you don't understand this concept, please watch my series of videos and watch the particular video on measures of variation, okay? So standard deviation is the square root of variance, all right? So anything that works for standard deviation, technically, it should work for variance. In other words, what I mean is that if the standard deviation of one variable is bigger than the standard deviation of the other, definitely its variance will also be bigger than the other. So you could work in standard deviation or you could work in variance, all right? Now, in this topic, we are going to estimate population variance. Remember, when you find the square root of variance, you get standard deviation. But that does not mean that variance is not a measure of variation. Variance is a measure of variation. Just that when you want to bring it into the standard form, you find the standard deviation. So for now, we are not going to bring it in the standard form. We are going to consider variance as a measure of variation or a measure of dispersion. As I've said, if you don't remember, just go to my series of videos and find a video on measures of dispersion. You understand this better. Okay. Now, we are going to estimate or we are going to do hypothesis testing for a single population variance. So somebody may ask, why do we need to test hypothesis for variance? The same way, sometimes when we don't know the population mean, we use the sample mean to do a point estimate, and then we can do a hypothesis for the sample mean. That is the same way when we don't know the variance of a population, we can use the variance of a sample to test hypothesis, all right? So up until now, we've been doing hypothesis testing for mean, for proportions, and then whether for mean or proportion, we've been doing it for a single population and a two or more population. So in this particular topic here, we are going to do hypothesis testing for variance, all right? We are going to do it for variance. So we are not doing it for mean or proportion, but we are doing it for variance, all right? So definitely when we don't know the population variance, definitely the sample variance will be the point estimate. But then, if we want to be sure that it's a better representation, before we make a conclusion. That will lead us into what we call hypothesis testing, okay? So we're going to do it for a single population variance. Then later, we will do it for a two population variance. Now, to do this, we are going to test the null hypothesis that the sample variance is equal to the population variance, all right? So we compare the sample variance with a hypothesized. So there's a sample variance, you compare it to the hypothesized population variance. Now, the assumption we make is that the random sample is from a normally distributed population. The distribution for the standardized sample variance is a chi-square distribution. So as I said, in this topic, we are not going to read the Z or the T to do the hypothesis testing. We are going to use the chi-square table to do the hypothesis testing. Now, if that is the case, it means that we have to know how to compute the chi-square. Then that will be our computed chi-square. Then we have to also know how to read the chi-square from the table, and that will be our critical chi-square, okay? So the same way we have the computed t-value and we have the critical t-value, that's the same way we also have the computed chi-square and then the critical chi-square. So if you want to compute the chi-square for you to compare with the critical chi-square, there's the formula for chi-square. So chi-square here is equal to the sample size minus 1, bracket close, times the sample variance, okay? Remember, standard deviation squared is variance. So sample standard deviation squared is called sample variance, all right? And then divided by the population variance. So that is how we compute our own chi-square. And then when we're able to compute our own chi-square, then we'll read the chi-square from the table, draw our graph, and then we'll now make a decision, okay? Now, similar to t-values, chi-square are also read from the table, and we will need a degree of freedom to read from the table, all right? So remember, when it comes to chi-square for a single population variance, the degree of freedom is n minus 1, okay? Because it's a single population variance, the degree of freedom is n minus 1, all right? So once you know your confidence level, once you know your alpha, okay, once you know your alpha, and once you know your degree of freedom, you can read the chi-square from the table to get your critical chi-square. Then when you compute your own chi-square, then you fix it in the drawing to check whether it falls within the acceptance range or the rejection rate. All right, so let's look at this example. This example says that a company does small moving jobs for businesses and private residential customers. Looking at past record, the operations manager has determined that the mean or the average job time for a properly trained moving crew is 2 hours, with a standard deviation not to exceed 0.5. Suppose the operation manager took a random sample of 20 service calls and find a variance of 0.33 squared. So we are going to test the hypothesis. Now, remember that looking at past record, the operation manager has determined that the mean job time for properly trained moving crew is 2 hours with a standard deviation of 0.5, okay? Now, the average time for moving crew, usually we cannot have a standard for this. So what it means is that the manager claims, okay, the manager claims that sorry about that. Really sorry about that. Sorry. Now, the question says, let's take it again. The question says that looking at past records, the operations manager has determined that the mean job time for a properly trained crew is 2 hours. Okay, so sorry, this is not a claim, it's a standard. The reason being that the manager has looked at past records, and that is what has been happening all these years. Okay, so sorry about that. It is rather a standard, not a claim. Sorry about my earlier assertion. So it says, looking at the past records, the operations manager has determined the mean job time for properly trained moving crew is 2 hours, with a standard deviation not exceeding 0.5 hours. So the fact that the question says looking at past records alone means that over the years, that is how the thing has been. And that means that it is a standard, all right? So the standard here is that the standard deviation does not exceed 0.5 hours, okay? So if standard deviation is equal to 0.5, the variance, which is the standard deviation squared, will be 0.5 squared, and it will be 0.25, all right? So here, the standard is that, the standard deviation, okay, does not exceed 0.5 hours. So when something does not exceed 0.5, means that it is 0.5 and below. It doesn't exceed 0.5, all right? So that is the standard. So this is the standard or the status quo. Okay, now, that is the standard or the status quo, okay? All right. So remember, we are testing hypothesis about variance, not standard deviation. So we have to convert the variance, we have to convert the standard deviation into variance. So variance is standard deviation squared, and that is 0.5 squared, and that is 0.25, all right? So our standard says that the variance, so we've now converted to variance. So the null hypothesis means that our variance should not exceed 0.25 because it's a status quo. So the status quo reflects in the null. Then the alternative will be the opposite. That means that our variance is greater than 0.25. All right. So this is basically the hypothesis we are going to test. All right. This is the hypothesis that we are going to test. Now, the chi-square table does not really look like the normal distribution table. All right, or the curve, sorry. So when this is the chi-square curve, all right? But in the question says that we are testing this hypothesis. Let's look at the question again. We are testing the hypothesis at an alpha of 10%, all right? An alpha of 10%, or a confidence level of 90%. If this is a case, if we want to draw this curve well, it means that we have to rewrite this hypothesis. So here, we are looking at the fact that the sample standard deviation is, we are looking at the fact that the population standard, the population variance is less than or equal to, so let me clean this. The population variance is less than or equal to 0.25. So you bring it here. So there's no need to rewrite, let's just draw it straightforward. So the population variance is equal to 0.25, all right, 0.25. Okay, so since our null hypothesis says that it's less than or equal to, it means that everything here is the acceptance region. But as usual, we allow for a little more, all right? We allow for a little more. Because it's less than or equal to, we allow for a little more so that everything here will now be the acceptance region, okay? Then the remainder here will be the rejection region. But then remember, we need to know the bound. So since alpha is 0.10, okay, and then if you look in the question, the sample size, if you look in the question, the sample size is 20. That would mean that the degree of freedom is 19. So in the question, the sample size is 20. The degree of freedom is n minus 1, so we are going to get 19. So our task now is that we are going to read 19 degree of freedom and alpha of 0.1 from the chi-square curve, all right? Now let me show you something about the chi-square curve. The chi-square table or the chi-square curve, the one I'm going to use in this particular video, whatever you read is one tail, all right? Whatever you read is just that tail, okay? Whatever you read is one tail. And then the chi-square distribution table, it breaks it into two, all right? So let me show you something. The chi-square distribution table is like a mirror. It's like a mirror, okay? So if you want to read 0.05 on the right-hand side, this is how we read it, all right? But if you want to read 0.05 on the left-hand side, as I said, the chi-square distribution is like a mirror. So that one, you rather read 0.95. It's like a mirror, okay? For instance, if you read 0.01 here, it means that if you want to read it from the other side of the story, on the left-hand side, it will be 0.99. So the chi-square table is like a mirror, where the other side is the other side of the probability, okay? So that's how the chi-square table works like. If the thing is in the positive region and you are going to read, it's 0.05. But if it's in negative region and it's 0.05, you rather read 0.95. So this table doesn't work like the conventional T and then Z table. This is a little bit different, so pay attention to it. I said if you're going to read it in the positive zone and it is 0.05, its corresponding in the negative zone will be 0.95. Now you read, all right? Okay, so here, because our graph will have to be read in the positive zone and alpha is 0.10, we are just going to read 0.10 from the chi-square table. On the assumption that we need to read it from the negative zone and the alpha is 0.10, we just read 0.9 because of the mirror issue. So for instance, if we are reading 0.10 alpha, okay, and it's in the positive zone, when you go to your table, you read 0.10 alpha. But if you are supposed to read something that should have fallen in the negative zone, okay, you rather read an alpha of 0.90 because of the mirror. This side reflects the other side, all right? So anytime you are reading a figure from the chi-square table and it's supposed to be in the negative zone, if your alpha is, let's say, 0.1, and the figure is supposed to be in the negative zone, you're supposed to read 0.9, all right, because of the issue of the mirror. So let's look at something here. So our alpha was 0.10 per the question. Degree of freedom is 19. Okay, so let's go to our chi-square table and go and read. So there's our chi-square table. So there's the chi-square distribution table. So this was what I was talking about. All right, this is what I'm talking about here. So because it's in there, so the 0.1 here, okay, the 0.1 here, its mirror is the 0.9 here. 0.05 here, its mirror is the 0.95 here, all right? 0.025 here, its mirror on the left-hand side is the 0.975. 0.01, its mirror is the 0.99, right? So here, because we need it on the right-hand side, you just read the 0.10. If it's supposed to be on the left-hand side, we would have read 0.9, which is the mirror of 0.10, okay? So I'm just going to read the 0.10 and the degree of freedom of 19. So the chi-square is 27.20. 27.20, all right? 27.20. So here, the critical chi-square is 27.20. Okay. The critical chi-square is the 27.20. That's the critical chi-square, 27.20. Now we are going to apply our formula and then compute our own chi-square. Then we will see whether it falls into the acceptance region or the rejection region, all right? Now, this is the formula for finding the chi-square by yourself, which I've already shown you, but let me just repeat myself for the purpose of emphasis, okay? So this is the chi-square formula. The chi-square formula is sample size minus 1 times sample variance all over population variance. So in our question, the population variance, remember, based on the hypothesis we stated, the population variance is 0.25. And the sample size is 20. So we have 20 minus 1. The population variance is 0.25, okay? All over, oh no, that is, sorry. The population variance is 0.25. Then in the question has given us the sample variance. So the sample variance is 0.33, all right? Because the question says, suppose the operations manager took a random sample of 20 service calls and found a sample variance of, so the sample variance is 0.33, okay? So once you fix them in the formula, you're going to get a computed chi-square of 25.08. You're going to get a computed chi-square of 25.08, okay? So when you come in your bigger diagram, 25.08 will be somewhere here. Okay, so 25.08, it falls in the acceptance region. All right, because it is less than 27 point, it's less than the critical one, so it falls in the acceptance region. Okay, so we will fail to reject. So our conclusion is that since the computed chi-square, this one is not an X, so it's a Greek alphabet, okay? It's not X, it's a Greek alphabet. The chi-square is a Greek alphabet, something like this. It's not like an X. So the chi-square, since the computed chi-square is 25.08, and it is less than the critical, it's less than the critical chi-square at 0.10 level, degree of freedom of 19, which gave us the 27.2036, okay, we fail to reject the null hypothesis and conclude that, so let's go and look at our null hypothesis. Our null hypothesis is that the population variance is less than or equal to 0.25, or the population variance does not exceed 0.25. So that was our null. So since we have failed to reject, you conclude that the population variance does not exceed 0.25. Does not exceed 0.25. So that is how we are going to test that hypothesis. Now let's pick another example, which is two-tailed. Let's pick another example, which is two-tailed. I think it will make it more understandable. Okay, so this question says that the company is experimenting with devices that can be used to store solar energy. Engineers have determined that one particular storage design will yield an average of 88 minutes per cell with a standard deviation of 6 minutes. They have also made some modification to the design and are interested in determining whether this change has impacted the standard deviation either up or down. Either up or down. So the either up or down simply means it's two-tailed. A random sample of 12 individual storage cells. So here it means that the sample size is 12. Containing the modified design have been used. So we are going to test the hypothesis together, all right? Now here, it says engineers have determined that one particular storage design will yield an average of 88 minutes per cell with a standard deviation of 6. So because engineers have determined, it's not really a claim, it is probably a standard. But even aside that, they are interested in testing whether the standard deviation will either go up or down. So this simply means that if the sample, if the population standard deviation, if the population standard deviation is 6 minutes, okay? If the population standard deviation is 6 minutes, it means the variance is 6 squared, all right? The square of standard deviation is variance, and so that will give us 36, okay? So our null hypothesis is that the variance is equal to 36. Our alternative hypothesis is that the variance is not equal to 36, all right? So here we are going to draw our chi-square table. Sorry, I'm going to draw our chi-square curve, okay? Now, if the variance is equal to 36, we will allow for a little more and a little less. So everything here is the acceptance region, and then the remainder here is the rejection region. All right. Everything here is the acceptance region, and the rejection is, the rest is the rejection region. Remember that this question is a two-tailed because the question said you want to find out whether the variance is either above or below the 36. So it makes it two-tailed automatically. All right. And always the equal to sign will come in the now. And I believe by now you know that, okay? And even engineers have determined that that is the standard. So the standard is 36. That's why it's even in the null hypothesis as well. There are so many ways you can know the null hypothesis in this instance. Okay. Now, let's look for the degree of freedom and then the degree of freedom and then as well as the level of significance. So here it says alpha is 0.1. Alpha is 0.1. Let's watch it carefully. So alpha is 0.1, okay? Alpha is 0.1. That means that half of the tail, each tail, half of it will be 0.10 divided by 2, which is 0.05, all right? Because we are testing at 90% confidence. Now the sample size is 12. That means that the degree of freedom is 12 minus 1. And that will give us 11, okay? 12 minus 1 will give us 11. Now, if this is the case, what it then means is that the chi-square distribution, as I told you, is always a mirror. So for the positive side or the right-hand side, we will read 0.05. Okay, chi-square of 0.05. But for the left-hand side, its mirror, listen carefully, its mirror will be a chi-square of 0.95. Okay, will be a chi-square of 0.95. That is how we read chi-square table. Always, if the alpha for both sides even was supposed to be 0.05, 0.05, usually you read the 0.05 for the positive side. Then the mirror, which is the 0.95, you read it for the negative side. That is how we read chi-square. It's a little different from the T table, all right? And I demonstrated it in the earlier example. So by now, you should be quite conversant with it. Now let's go to our chi-square table. So remember, the degree of freedom is 11, all right? So you're going to read 0.05 as against 11. And that is 19.68. 0.05 as against 11 is 19.68. So 0.05 as against 11 is 19.68. All right? Is 19.68. That's for the upper bound. Then 0. To the mirror of the left-hand side. 0.95 as against 11 is 4.57. So remember these two figures. The lower bound is 4.57. The upper bound is 19.68. All right. So let's remember these figures. So 4.57 and then 19.68. So we have the critical chi-square here is the upper bound is 19.68, okay? And the lower bound for the chi-square is 4.57. Good. Now, the next thing is that we have to compute our chi-square, because this is what we've done is the critical chi-square. So we have to now compute our chi-square. Okay? The formula for chi-square, as we already know, is n-1 times the sample variance all over the population variance. So here, n-1 is 20, the sample size was 12 minus 1 multiplied by the sample variance all over the population standard deviation. Remember, the population standard deviation is 36. From the hypothesis we wrote, is 36, okay? So here, we are going to have 36 here. And in the question will definitely give you the sample standard deviation or the sample variance. If it gives you the sample standard deviation, you have to square it. But if it gives you to get a variance, but if it gives you the sample variance, you have it. So the sample variance is 26.6. That's the sample variance, 26.6. Okay. When you work out everything here, you are supposed to get around 8.13. All right. So this is the computed chi-square. So let's go and fix it in our table. 8.13 will definitely be between. Okay, so 8.13, that's the computed chi-square, will definitely be between our upper bound and our lower bound, okay? So we would not reject the hypothesis. So let's find a better way of writing it. I'm going to say that since the computed chi-square is equal to 8.13, and it is between the lower bound, chi-square. The lower bound chi-square will have 0.95, right? And when we read, it was 4.58, okay? It is between the lower bound chi-square and the upper bound chi-square, that's 0.05, is equal to 19.68. We fail to reject the null hypothesis and conclude that what was our null hypothesis, because we have failed to reject, okay? So and conclude that the standard deviation is equal to 6, or you can conclude that the variance is 36. So anytime you fail to reject the null, your conclusion will be based on the null. You use the null to conclude. But anytime you reject the null, we use the alternative to conclude, all right? So this will bring us to the end of this video. In my next video, I'll teach hypothesis testing for 2 population variants, all right? Kindly like, share, comment, and then most importantly, please subscribe to my channel. Thank you.